So the next topic we're going to work on in this unit on momentum and energy is work and power. So these are words that we use every day in our lives, right? We get up and go to work, or how much power we feel we have. But what do they really mean from a physics standpoint, right? We might see some images like this and say, wow, these people are doing real work, right? Or off we go to the office, right, on a Monday morning, or off we go to school on a Monday morning, or off we go to our Zoom classes on a Monday morning, right? But different meanings for work and power. But today we're going to see how do we define that from a physics standpoint? Okay, so let's look at our objectives. First, how do we define and then calculate the work done? And second, how do we calculate the power? And what's the relationship between work and power? So let's dig right in. In order for work to be done from a physics standpoint, two requirements must be in place. The first is that we have to be applying a force, okay? And we've been doing lots of work with different types of forces, right? Gravitational force, normal force, push-pull forces, normal forces. So the first is that we have to be applying a force to perform work. Okay, so here's an example, right? Lifting up the barbells or pushing a box across the floor. And then the second requirement is that when we apply that force, we have to move an object some distance. Okay, so if we're just applying a force, but there's no motion involved or movement, then there is no work being done. Likewise, if an object is moving across the floor with moving across some distance, but no force is required to get it to do that, then again, there is no work being done. So let's look at some examples here, right? If the weightlifter lifts up those barbells a certain distance, then he's doing work. If he's just holding the barbell at a certain position without moving it, there is no work being done. Same thing with the crate, right? If we move it across the floor some distance, we are doing work. Now, how do we actually calculate work? Well, it's quite simple. Work is equal to the force exerted on an object in the direction of motion times the object's displacement. Okay, so basically force times the distance. And the assumption here for most of the problems we'll work on is that the force, being a vector quantity, is in the same direction as the object's displacement, how far it moves. They're both in the same direction. Okay, it's only that component of the force that is in the same direction as the displacement that counts when we include it in this calculation of work. So notice the units here. Force would be in newtons, distance would be in meters, or displacement is in meters. But we also have another name for work. And you probably have heard this before, particularly think back maybe in your chemistry classes. We call that a unit of work is often referred to as a joule, Joule, and we use capital J as the abbreviation for that. Now you may say, wait, I thought joule stood for the units of energy, and you're correct. We'll get to energy in the next lesson, but it turns out that work and energy are interchangeable. They are equivalent to each other, at least in terms of the units that we use. So 1 Newton meter is equivalent to 1 joule, right? So if we applied a force of 1 Newton and had a displacement of 1 meter, that would mean that we did 1 joule's worth of work. Work is a scalar quantity, even though force and displacement have a direction associated with them. Once we multiply them together, all we care about is the magnitude of the work being done, no direction. So let's go back to our example here, right? If we had a weightlifter and he applied a force of 3 newtons and lifted those weights a distance or displacement of 1 meter, how much work did he do? Well, it's just simply 3 times 1 Newton, right? The force is in the same direction as the displacement. So we would say the weightlifter did 3 joules worth of work. Now, how about pushing the crate? If we pushed with a force of 1 Newton for a distance of 3 meters, again, we would just multiply the force times the distance and get also 3 joules. Okay, so the math is simple, right? Force times distance. We just need to make sure the force is in the same direction as the distance or displacement. Now, work can kind of fall into 2 categories. Or if we think about it in terms of types of problems that we'll solve, the problems will fall into these 2 categories. So the first is work being done against another force. So if you think about those previous examples, right, lifting a weight up, what force are we doing work against? Well, we're doing the work against the force of gravity pulling down. Or pushing a box across the floor, if it takes some force to do that, that would imply that there's friction, right, that's pushing the other way. So we're working against another force. Okay, so doing push-ups, right, would be an example of doing work against the force of gravity, or pushing an object to overcome friction. The other case is work done to change the speed of an object. Okay, so if we apply a net force and it causes the object to either speed up or slow down, that is another form of applying work to that object, okay, or doing a certain amount of work on the object. So an example, right, if the car accelerates, the engine's doing the work to speed it up. If we bring it to a stop, the brakes are doing the work to slow it down. Now, let's talk about power and how it's related to work. So power is the rate at which work is done. Now, when we say rate, we mean the rate with regard to time. So power, we use a capital P for power, equals the work divided by the time it took to do the work. Okay, so it's simple. Once we know the work, let's say we did a certain amount of work for 20 seconds, we would just divide that by 20 and get our power. Now the units for power would be joules divided by seconds, and we have a name for that unit. It's called a watt, and I'm sure you've heard of that before, right? There's lots of electrical appliances that we buy often that says uses this much power, so many watts. It used to be our light bulbs, right? Were rated by the wattage on them, a 100-watt light bulb. Now that we have LEDs, it's a little different, right? They now rate them in terms of lumens. It's a different measure. It's actually a better measure of the amount of light being produced. But another good example where we use that is how we pay PG&E for our electricity that we use, right? The meters will read how many watts we use over a period of time. So some common units of measure that we might see is a kilowatt, which just means 1,000 watts. 1 watt is a pretty small amount of energy, or power rather. So often we'll see kilowatts as the preferred unit of measure. Megawatts, sometimes we might talk about, say, the amount of power that a power generation station uses or generates, or a big city might consume in terms of power. That would be 1,000,000 watts. Now, you often probably hear the term horsepower, right? Now, this is literally a 1 horsepower car. I guess this is what happens when the engine dies and is of no use to you. You can still use the back of the car as a horse buggy. So this would somewhat jokingly, right, would be a 1 horsepower car here. But how much is a horsepower, right? Because we know how much a horsepower or engines and cars are rated by horsepower. It turns out the 1 horsepower is the equivalent of about 750 watts. Okay, so not a huge amount of power, but as we'll see in some examples, that would be a great amount of power for a human being to generate. Even some of our top athletes can barely generate 1 horsepower worth of power for a short amount of time. Okay, let me go past this here. let's look at some examples here where we're going to calculate both the work and the power. So I don't know if you know who these guys are, Fred and Barney, right, from the Flintstones. Big when I was a kid. I don't know if they still are. But we have a net force of 2,800 newtons accelerates a 1,250 kilogram vehicle for 8 seconds. The vehicle travels 80 meters during this time, right? So this is Fred and Barney paddling with their feet here is what's applying that force. So we want to know two things: how much work is done on the vehicle by Fred and Barney, and how much power does this represent? How much power are Fred and Barney generating during this time period? So let's put down what we know, right? We know the mass, we know the force that is being applied to the car, we know the distance that the car travels, 80 meters, and we know the time period, 8 seconds. Okay, what we're trying to find are the work, W, in joules, and the power in watts. So let's go to our formula, right? The first for work is simply force times distance. And unless it states otherwise, we'll assume the force is in the same direction as the distance or displacement. So we just need to multiply those together, 2,800 newtons times 80 meters. And we do that, we get a pretty large number, 224,000 joules worth of work are being done by Fred and Barney on this automobile. Okay, so we have the work. Now let's find the power. So remember, power is just the rate at which the work is done. So once we know the work, we're just going to divide that by the time period. So we know that the total work was 224,000 joules, and we're going to divide that by the time, 8 seconds. And so we get this figure, 28,000 watts, or we could say 28 kilowatts, right? Because 1 kilowatts equal to 1,000 watts. Okay, so quite a bit of power being generated there by Fred and Barney. Maybe not that realistic of an example. Let's look at a little more realistic example here, okay? And if we were together in class, I would actually have you do this. Take a brick and lift it from the floor as high as you can over your head, as quickly as you can. And then we can calculate how much work you've done and how much power you generated. So since we can't actually measure that in a classroom, I've given you some values here. So it says the brick is 6 kilograms. And when you lift it as high as you can over your head, that gives us a height of about 2 meters. And then we're going to lift that brick 10 times, and it takes us 30 seconds to do that. So let's list what we know, right? We know the mass. We don't know the force directly, but this is an example, right, of doing work against another force. And in this case, that force is the gravitational force, right? When we lift that brick, we have to apply a force equal to or slightly greater, right, than the force of gravity in order for us to have it move upwards, to accelerate upwards. So what would that gravitational force be? Well, it's the mass times the acceleration due to gravity. So 6 times 10 gives us 60 newtons. The displacement is 2 meters from the floor to as high as we can hold it over our heads, and it takes us 30 seconds to do that. Okay, so back to the same calculations. Work is force times distance, so we have a force of 60 newtons times 2 meters. Now that would be the amount of work that we do in one lift, but notice in this problem, we're lifting the brick 10 times, so we're going to multiply that by 10. Now you may ask, what about when I lower the brick back down to the floor? Well, in that case, we're really not doing work against gravitational force, right? We're just kind of controlling the rate at which the brick falls back to the ground, right? We're not having to work against gravity. We're letting gravity basically pull the brick back to the ground. So the only work that'll be done is when we're lifting it upwards. So we multiply that total by 10, and we get 1,200 joules. And notice, it doesn't depend how long it takes us to do that, right? Whether it take you 30 seconds or 3 minutes, it would be the same amount of work. It's the power that depends on the time, right? So let's take that work of 12,000 joules and divide it by the time, 30 seconds to lift that. And we would see we would generate about 40 watts here. So that's a little better example of what in our everyday lives, the amount of work and the amount of power, right, that a typical human can apply or generate. All right, so that's it for work and power. We know how to define and calculate work, force times displacement, and we know how to calculate power. It's the rate at which we do work, work divided by time.